From the machine learning department. He's going to talk about some of his recent work.
So, hi everyone. Thank you very much for coming for the food and the talk. It's not as crowded as I suppose. That's much better for me because I get very nervous for this. So today I want to introduce the sigma optimality, which is an optimality criteria we have proposed, and I want to talk about its application in active learning on graphs, and the representation for the graph model is Gaussian random fields. This work is done by me, by Roland Garnett, who used to be a postdoc here, and by Professor Jeff Schneider, who is my advisor. So the task we want to solve is the active learning on a graph. That is, we're given a connected and undirected graph. We know its nodes, we know its edges. Maybe this is an example of a graph, but you actually get a much larger one. And some edges may have weight, or you can deal with graphs that do not carry weight. And we want to query k labels so that we can best predict other labels. So there's a decision to make here, which k labels we want to query. And the labels are categorical. We just take the labels to be binary for now. This is a categorical label. There are 3 classes, but in the nature I'll just assume 2 classes on the graph without other mentioning. Yeah, so the question is, which k labels we want to pick? This is a canonical active learning problem. So I have introduced the problem. Then I will talk about the model for the graph, which is a Bayesian inference model called Gaussian random fields. I will talk about the heuristic to select these k nodes, which is basically variance reduction. There's V optimality and sigma optimality. Sigma optimality is the thing we are crazy about. And then this selecting k nodes is a set optimization problem, and usually it's computationally intractable. So I want to talk about a greedy update, which is an approximation to the set optimization problem. And I want to talk about its algorithm, its theoretical bound, and intuitions. Finally, I want to talk about some other observations and some empirical results. So here are some terms we use throughout the talk. There's this adjacency matrix, which characterizes the existence of edges between nodes. There's a little bit unconventional diagonal matrix D, which characterizes the degrees of nodes in the graph with no weights, but only uniform weights. And mathematically, it's the diagonal of the vector of row sums of A. Because we are addressing undirected graphs, so it is also the column sums of the A. And we have this propagation probability, which is D inverse A, the row normalized version of A. We have a graph Laplacian, D minus A. We have the set, this curly L, denoting all the nodes that we query for labels, and this U denoting all the nodes we want to predict. And finally, we want to partition the matrix A so that A subscript curly L, A subscript U are submatrices, and A LU, AUL are vectors. We partition A, D, L, P in the similar way. So here's the Bayesian inference model behind the graph. Suppose, well, in a graph we know its labels, but let's just imagine these labels are generated in this way. So there's a prior. This prior says if node A and node I and node J are connected through an edge, their labels and their labels are similar, then you get a higher probability for this type of distribution. So there are also other ways to introduce Gaussian random fields, but I'm just introducing this through the Bayesian inference framework. The likelihood, so interrupt me if you have a question. The likelihood is exact inference. That means when you compute the posterior, you basically take all the nodes that you have labels and you factor them out of the distribution probability. So you get this posterior. You take all the nodes associated with curly L and you just move them out. You just throw them out. And you get this. Approximately, this is a normal. This is not exactly a normal because this is a binary output. But approximately, you can see it as a normal. Now this is a model we'll use. So how do we compute the posterior mean? Here's an iterative algorithm. It's pretty much in a way similar to a page run. You initiate with your guess at 0, and every time step, your new estimation about the posterior mean is in this form. And if you take t to the limit, basically you take t equals to t minus 8t plus 1, you get this stationary distribution, and this gives us back the form of the posterior mean. So there's a caveat here. I always thought in the beginning that this is a label propagation, but actually it is not exactly, because the P is D inverse A, which is row normalized. And if you are doing label propagation, you would prefer a column normalized matrix because you want to have equal weight for outgoing edges. Here you have an equal weight for incoming edges because you're row normalized. However, if you take the reverse, you do a random walk from this yellow node I, right? And this posterior mean basically says the chance that a random walk starting from I will hit a labeled node with label 1 before it hits a labeled node with label 0. So this 1 and 0, this brown colored nodes are the labeled nodes. So I'll hint, if you want to do multi-categorical classification, basically you will predict the label of the node I based on which class it has the highest chance to hit first. So that's for multiple classes, but this is only for a binary case. And it can also be interpreted in the resistor network. And if you supply 1 volt to the labeled nodes with label 1, you supply 0 volt to the nodes with label 0, then your posterior mean is the voltage at this node. Also, we can compute the posterior covariance matrix. Here I'm using the Gaussian approximation to the posterior. Basically, you can take this into multiple steps, and you can do a fast approximation for the posterior covariance matrix. So we've covered the model. Now let's talk about variance reduction. If we look at the posterior, we can see several terms. There is this yu minus e of yu. That says if there is truly a true underlying model, latent variable ey for this observation y, then there is this intrinsic uncertainty or this risk that is unavoidable. And there's also this bias, and because Gaussian random field is a Bayesian inference model, there's really no way to track the true mean from a Bayesian inference model. But however, if we accept the Bayesian assumption, we accept that all the nodes are generated in the way we described, then this will naturally be 0. Finally, we have this variance. And this variance is really the tool we use to control the posterior, the uncertainty in the posterior. And how will this variance help us in decide which k-nodes we want to pick in our active learning problem? So in statistics, there are a lot of optimality criteria for experiments design that are based on variance reduction idea. And I want to introduce you one, which is called V optimality. And we will put up one more, which is sigma optimality. This V optimality, there are two ways to interpret the V optimality. One way is directly, we want to minimize the trace of the predictive covariance matrix. That is the average predictive variance I've explained in the previous slide. Another way is through L2 risk reduction. The L2 risk is the average risk L2 loss of the unlabeled nodes between the true label and the posterior mean. And if we take the approximation to say the true label is really just a distribution, then this L2 risk will again give us back the trace of the inverse covariance, posterior covariance matrix. Sorry. This is work by Zhu et al. In 2003. It's also recently appeared in ICML and for its practical efficiency. So in order to for us to put up one more optimality, I need to mention another task that this sigma optimality is originally designed for. This task is active surveying on a graph. Still, we have this nice graph. And here we want to query k-labels to predict class proportions. So again, don't be fooled by this graph. I'm not dealing with multi-class problem for now. I'm only dealing with binary class. So basically, you just want to compute how many nodes are labeled as 1, how many nodes are labeled as 0. That's the active surveying graph simplified form. For this active surveying problem, if the posterior is this Gaussian, then this posterior for class proportion in a binary setup is simply the average of the posterior. I took the sum of the posterior, I took the sum of the YU because they are basically the same thing. For this problem, you can also do a risk minimization step. And the risk is this variance of the posterior for the sum of YU. Basically, this is just a number. So we proposed the sigma optimality in this form. We want to minimize the set L so that this risk, the grand sum of predictive covariance matrix, is minimized. Okay, so here's are our two optimality criteria. One is V optimality, one is sigma optimality. Hope you all understand this guy. So let's take a vote. Which one do you think gives us better choice of k-nodes in the context of active learning problem, active classification problem? Who votes for V optimality? Okay, 3 votes. Who votes for sigma optimality? 4 votes. So it's a bit unclear. Do you have a question? No? Cool. So I'll just address something more. This is a set optimization problem. This is intractable. We need to come up with a Brady sequential update algorithm. And this algorithm works like this. You select your first k nodes first, and then you pick your next node to add into the set that you want to query by the marginal contribution of this node, by how much further this node can reduce your risk. And for V optimality, the risk is the trace. For sigma optimality, the risk is the grand sum of the predictive covariance matrix. If after some mathematical computation, you can see the sequential step winds up being in this form. I won't show you the details, but you just trust me with this. And here are two new notations I need to explain. Rho Vt is the correlation between nodes V and T conditioned on all the k nodes that we have previously added to our set. This sigma T is also, sigma T squared should be the variance.
I have a quick question.
Sure.
Does L depend on the actual labels? It doesn't, right, of the labeled set?
That's an excellent question. For this problem, it doesn't.
So in what sense is this active learning, right? Because you could pre-plan which labels, given the graph and the relationships between nodes and the unlabeled graph, it seems like you could just pre-plan which nodes you want to query for labels. If L does not depend on the labels, the actual labels you observe from the querying.
That's a good question. I think that's just yeah, I don't know. Just by convention, people just call this algorithm an active learning algorithm.
Yeah, I mean, I think that's fine. In this, for this particular model,
Yeah.
you could pre-plan the whole thing. But for some other model, you might actually depend on labels. That's okay.
Yeah, in terms of this optimality criteria, they also apply to other active learning problems, which you really need to, or I don't know, it's tough offline.
Sure.
Okay, so we still have this problem of whether V optimality works better or sigma optimality works better. But before doing that, let's have this theoretical guarantee between the greedy sequential selection algorithm and the set optimization problem. Because ultimately you want to solve the set problem, but there's this greedy update approximation. So can this greedy approximation be really an approximation for this sigma optimality, for these set optimization problems? So for V optimality, first we come up with a proof that appeared in NIPS workshop last year. And then we found there's also this work by Fred and Gilbert in the statistics community. They address all the spectral set optimization problems. The spectrals for Gaussians. The trace of the predictive covariance is one spectral predictive covariance, spectral function on the predictive covariance matrix. However, for sigma optimality, this is not a spectral function. And we came up with something else, which basically on the same idea as the previous one, and we put it on archive. So what this bound says is the risk reduction through the greedy choice of k nodes. Usually it's not as good as the global optimum. But it is not too bad from the global optimum. It's worth the global optimum by a constant factor. This proof is done by showing the submodularity and a monotonity for the risk reduction.
Is that E like Euler's E, or is that some number that we don't know?
Oh, just the summary. Yeah. the natural log. Yeah, the natural E. Right. And by the way, if you show this is a submodular monotone function, then you get this bound for free. There's this well-known result. And now let's address the problem, which one works better in active classification problem. It turns out that sigma optimality actually works better. Here's why. First, let me explain that V optimality actually is doing something. If we ignore all the set optimization and the approximation to the set optimization, we just look at the greedy sequential selection algorithm. There is an intuition behind this. This says we want to pick, if we're given k nodes, we want to pick the next nodes to query so that the next node V is highly correlated to a lot of nodes T which have high variance. So the sum of square of this is basically the correlation times the correlation squared times the variance. So V optimality is choosing the node that does this. And sigma optimality is similar, but you just put the sum to the inside. And so question, why this buys you something? It turns out this is exactly V optimality plus this cross product between terms. Between T1 not equal to T2. So I have to say that those T's, T1s, T2s can be the V node itself. Right. So by writing it out in this form, we have this cross product. And by Cauchy-Schwarz inequality, this cross product is maximized when the both terms are roughly equal. And that means we not only want our next selected node to have a strong correlation to the high variance nodes, but we also want this correlation to high uncertainty nodes to be universal, to be equal. And here is a toy example showing what I mean by this. This is a graph, and V optimality, if I give the budget 3, V optimality selected this node first, and then this one, and this one. So it selected the outliers, because by knowing this node, your uncertainty about this node is still very high. And in this particular graph, it thinks that by querying these nodes, it addresses the uncertainty the best. However, using sigma optimality, it not only wants to reduce its own covariance, its own uncertainty, and the uncertainty of nodes connected to this one or related to this one. It also wants to reduce the uncertainty globally. So it naturally picks the cluster centers. So, question?
Yeah, so this shows that your greedy procedure for sigma optimality is better than the greedy procedure for V optimality.
Yes.
Does that necessarily imply that sigma optimality is better than V optimality if we do global optimization?
I don't know, but in practice, you never do set optimization for this type of problems because the computation is unaffordable. So I haven't thought about this, but I don't think it really matters.
In some ways, if sigma optimality was actually better even for the set problem, that would be even more shocking, right? Because V optimality is minimizing the risk of what we're going to measure. So that would really be shocking. But,
Exactly.
but I think we don't know for sure. But
I mean, that's why from the beginning I voted for V optimality.
right.
And so now it's still like sigma optimality is better. Oh yeah, it's counterintuitive. So maybe it's because of the procedure rather than the formulation.
Right.
And we have some other observations about Gaussian random fields. One thing I want to point out, one other observation is the suppressor-free condition. This condition is also approved for the submodularity of set risk reduction function, and also approved for the theoretical bounds we have. So, but we need to, if we go through this path of proof, we need to prove suppressor-free condition first. And what this says intuitively, I need to thank Peter Huggins for pointing out this intuition. It says it is basically a decreasing correlations condition. So we all know for Markov random fields, if you label all the Markov blankets between two nodes, then the two nodes becomes independently, conditionally independent. Now for this model, Gaussian random fields, actually even before you form the Markov blanket between the two nodes, their correlation still becomes smaller. Notice this is correlation, this is not only covariance. And this is not too trivial because the set, otherwise suppressor-free condition is sometimes occur in statistical problems, and it's hard to visualize. It's hard to give an example. So here's the proof why this happens. It's very, this proof is strongly related to the very nature of Gaussian random fields. So because in Gaussian random fields we use this graph Laplacian, and we can expand by computing the predictive covariance matrix, the inverse of a subset of graph Laplacian can be expanded in this form. And the probabilities are all non-negative, and this degree matrix is also non-negative. So LU inverse is non-negative element-wise. Also, if you apply Schur's complement, you get this form. And so this part is the inverse of the lower right submatrix of L. So this part also becomes non-negative. And L11 inverse is the inverse of the upper left submatrix of the graph Laplacian. And by the first bullet, it is also non-negative. Finally, this L21 and L12 is the off-diagonal element in the graph Laplacian, so it is also non-negative. Here, L itself is a subset of graph Laplacian. Otherwise, we would get non-singular. So we can't do inverse if it's not singular. If it is a question.
Just some intuition. Do you have an intuition on whether the suppressor condition would be realistic for non-Gaussian problems that you would see in practice, or is it the other way around?
So even for Gaussian problems, this suppressor-free condition disappears for general case Gaussian processes. Does that answer your question?
Yeah,
Okay, cool. And this correlation, you can expand this correlation in this form. And this is the submatrix of set U slash T. T is an element set. And every term is non-negative. And because the bullet 2, they decrease as the U shrinks, as the set U shrinks. So as U shrinks, you get the smaller correlations. And the proofs for the submodularity is essentially the same. Again, I write this for V optimality. The marginal reward for the additional node V is in this form, and everything here and here decrease element-wise as the set U shrinks. And for sigma optimality, it's basically slightly different, but the same idea. So let's look at some experiments. This experiment is done by DBLP co-authorship graph, and this is weighted graph, It has 4 classes. This triangular shaped is what appeared in the 2012 paper for people promoting V optimality. And our sigma optimality beats their V optimality. Yeah, win. And they both win over random, which is a good sign. Honestly, in a lot of active learning problems, the algorithms won't beat random. And sometimes, I didn't show you, but there might be some mistuned. I'll talk about that later. There's also this 2 citation graphs, and this is Cora, this is CiteSeer, which are both benchmark problem sets. And on the left, there are 7 classes. On the right, there are 6 classes. And you can see sigma optimality still beats V optimality at random. Yeah.
By random, you mean observe a random set of labels and then infer the rest. Not like just randomly put labels on everything.
Why would it
I don't know. That's one option.
I would get a flat line.
Okay.
Yeah. Yeah, randomly selecting the K nodes. And then there's this active serving problem I talked about midway through my talk. Sigma optimality does its job. It basically says that. And here you can see the random actually works pretty well. And that's also intuitive because you basically want to know how many proportions belong to every class. So if you just do a random poll, you will actually get a pretty good idea. So randomness actually is a very strong opponent. So that brings us to the overview and future work. I've talked about the problem I want to solve is active learning graph, and we talked about Gaussian random fields, variance reduction, 3D updates, other observations of our graphs, and empirical results. So some future works or ideas include Christos Konotos. When I talked to him, he inspired me about this giving coupons idea. It's not a canonical active learning problem, but it's very similar to a binary classification problem. Basically, you want to give coupons to K nodes, and the relationship or the correlation between nodes, which in this term are the peoples, can be characterized by this graph. And somehow, if you give coupons, you can expect their friends can give you positive feedback. That's the basic idea. And we haven't addressed how to learn the graph. We only addressed how to infer labels after the model. And there's, since we have come up with this sigma optimality, which is basically just a general rule for active learning or experiments design in the statistics language. So is it possible to expand this to Euclidean space and regression problems? Here, you want to actually, the key thing here is to learn a good graph out of a Euclidean space. And we haven't really thought about how to do this. And finally, we want to incorporate meta-node information. That means for every node, there's not only the graph, we also, the nodes, for example, if we are looking in the Facebook network graph, the people, not only they have their network, which are important, but also the people also have their own posts or other features, and how do we incorporate these features into the prediction and active learning. And that's all. Thank you very much. Yeah.
So V optimality is optimized for the empirical risk or the expected risk, something like that, right?
Yeah.
And it seems like sigma optimality is optimized for something like 1 standard deviation above the expected risk, something like that, because it's modeling all the correlated risks of the tightly clustered nodes in some sense. So in some sense, it's be more careful about which nodes it selects. I don't know if that's an interpretation you can formalize, but so it seems like it's doing.
One step further from variance reduction.
Instead of the expected variance reduction, you're saying do something like, I want to minimize the worst case scenario where the variance reduction, where it's not the expectation, but one standard deviation above the distribution of possible variance reductions. But maybe we can talk about it something.
Oh, okay, yeah. Like a Bayesian hierarchical Bayesian. Question there.
Two short questions. Did I see in the charts that for really low budgets, random outperformed some of the others?
It's like one standard deviation.
Sorry, which graph?
I think in some of these graphs, the random for small budgets, random never did better. Right?
Oh, yeah.
Oh, no, here it did.
Yeah.
Is there some intuition why random might do better for small budgets?
Well, in the very beginning, it basically wants to pick a node with high degrees. And in this particular graph, the node with high degree really is just one person who does database in UIUC. And this professor cooperates with a lot of different people in different fields, so I get a pretty bad start.
One other question is, do you think there would be any point to minimizing instead of the sum of the classification errors, like a weighted sum, maybe corresponding to like an eigenvector or covariance matrix or something like that?
Why would a weighted sum be the
I guess, well, to generalize sigma optimality, is there something very special about using a vector of all ones, or do you think if you knew the right choice of weights other than ones, you could get better results?
Ooh, that's interesting. I hadn't thought about this. Yeah, if you have a weight of like which nodes you need to be more careful about, yeah, I think, yeah, it would be natural.
If you somehow, like a guess.
But you have to you have to engineer for this vector.
Yeah, you'd have to have some sense, you'd have to have some guess of what you think the covariance matrix is to begin with or something.
I think that will also be helpful for the incorporating meta information about the nodes.
Yeah, that might be one.
Thanks. Question?
Looks like that's it.
We should compute the actual
Think about
because really he's probably right. Probably the true he is right. It's only because it's only that updates for sigma. We